In the silent pulse of silicon grain, where numbers dance in a binary chain, a 0 seeks light and 1 seeks the shade to flip the script that the logic has made. Not a total eclipse, nor a ghost in the wire, but a targeted spark, a controlled beat of fire. We mask out the void, we toggle the state to find the complement and seal its fate. Welcome everyone. Today we are going to dissect a fundamental coding challenge, the complement of a base 10 integer. While it sounds like a simple math problem, it's actually a brilliant exercise in thinking like a computer. We will explore why standard operators fail us here and how to build a custom solution using Bitwise logic. Let's start with the basics. In the world of binary, a complement is a mirror image. Wherever there is a 1, we want a 0 and vice versa. Take a look at the table. For the number 5 represented as 101, the complement is 010, which equals to. Simple, right? But notice example 2. If we have 7, the complement is 0. This tells us something crucial. We aren't just flipping bits, we are flipping bits within a specific window. The size of that window is defined by the number of bits it takes to represent our integer. Here is where most developers trip out. In C++, an int isn't just 3 bits, it's usually 32 bits. If you use the standard NOT operator, the computer sees those 29 leading zeros and flips them into ones. Suddenly your small positive number becomes a massive negative value because that first bit, the sign bit, is now 1. To the computer, that's a signal for a negative number in 2's complement. To solve this, we need a surgical approach. We need to tell the computer, only flip bits in this specific range and leave the rest alone. How do we perform that surgical flip? We use a bit mask. Think of a mask like a stencil. We want to create a sequence of ones that is exactly the same length as our binary number. For the number 10, which is 1010, we want a mask of 1111. Why? Because of the magic of the XOR operator. In binary logic, XORing any bit with a 1 acts as a toggle. If the bit is 1, it becomes 0. If it's 0, it becomes 1. By XORing our number with our custom built mask, we get our complement without touching any of those pesky leading zeros. Let's break down the assembly line for this solution. The 0 guard. Since 0 is a special case in binary, we handle it immediately by returning 1. The mask builder. We create an empty mask and copy of our number. The discovery phase. We look through the bits. Every time we find a bit in our number, we add 1 to our mask. We do this by shifting the mask left and using a logical OR. The final toggle. Once the mask is the perfect size, we apply the XOR and return the result. If you look at this pseudocode, you will see the beauty of bit shifting. The line mask assigned mask left shift 1 or 1 is how we grow our stencil. It's like pushing a line of people to the left to make room for one more person on the right. We keep doing this until our temporary variable t hits 0, meaning we have accounted for every bit in the original number. Now let's look at the C++ code. Notice we use unsigned int for the mask. In C++, shifting bits into the signed bit of a signed integer can cause undefined behavior or crashes. By using unsigned, we ensure a smooth logical shift. This code is big O of log n, which in plain English means it's incredibly fast. Even for a number as large as billion, this loop only runs about 30 times. It is the definition of high performance code. To conclude, let's talk efficiency. In terms of time complexity, we are bound by the number of bits. Since the number of bits grow logarithmically as the number of n increases, our complexity is big O of log n. In terms of space complexity, we are big O of 1. We aren't creating arrays or complex structures. We are just using a few bits of extra memory. This approach is optimal, robust, and handles the leading zero trap that catches so many programmers. Thank you for your attention.